Hello, welcome to another problem session. I have a very interesting problem today, and it's simple and complicated at the same time. If we follow some of the basic definitions correctly, we should be able to get this right. Okay. This problem appears in many places. I think you can study more of these kinds of things at this website. Physics bootcamp.org. Okay, so what do we have here? So we have some shaft which is kind of at the bottom here. Can rotate. You can rotate this whole thing as one body there, and then there is a axle for this disc that attached rigidly to the shaft. When the shaft rotates, it kind of carries the axle with it. As the axle is carried, over here there are ball bearings that cause this to rotate about the axle, and this disc can actually go around in a circle, and that radius that it goes around, radius r, capital R, and the radius of this little disc is little r. Of course, if you go once around at this velocity, you're going to go several times around because this disk is smaller compared to the circle radius. So this little r is less different than capital R. You can have large radius r, so you go only few, but normally you will have this r is smaller than little r is smaller than capital R normally. So this is a question, and maybe you want to try to work on it. Just as a hint to before you go work on yourself is that this is this kind of a spin motion, and this is in an orbit. So this is like an orbit motion. So this is called orbital, and this is called spin, angular momentum. And there will be you have to think of L as a vector, okay? And it's going to have contribution from this motion and this motion. So this motion has vector that way, and this motion has vector that way. So you have to add these two vectors to get a total angular momentum, direction, as well as magnitude. And then for kinetic energy, I'll give you a hint. Kinetic energy will be kinetic energy of the spin motion and kinetic energy of the orbital motion, which is the only two motions here. And so you have to add the kinetic energy to get the total kinetic energy of the disk. Okay, so let me pause and okay, we're back. So let me do A. A would be, how would I do A? Well, imagine if you go in once around, how many times will this go around? So say n times this goes around in one time around this way. Let once around big circle, number of turns of disk equals to little n. So you can see the distances time, let's say time taken is delta t. So I got to figure out how much angle will be the same. So from here, you know the distance will be, when I go 2 pi r is equal to 2 pi little r times n. That's just, this is just basically that, right? So the n is simply r over r. Yeah, therefore the angle, let's see, this angle is called delta theta around here. So delta theta will be 2 pi for each turn times n. Okay, so now we need to make a delta t. Delta t will be, since I went one time around and it's going with omega, so delta t will be 2 pi over omega, just from the definition of angular velocity, right? So I got delta t and delta theta, so these two together, I can get a little omega equal delta theta. Theta is the rotation in the disk, delta t, and you can see how you have a 2 pi, let's write down the whole thing, 2 pi n over 2 pi over omega. So this cancels out, and this is n times big omega, and n is just r over r, a little r, omega. So the omega is r over little r times big omega. We assume that this thing is given. We're gonna say this is the relationship, and for the rest of the problem, we're gonna say assume we know omega, okay, and write all answers in terms of this. All right. Okay. So that's part A. And let's erase that and get more space for part B's and C's. Okay, so part B, what we're gonna have is, for part B is gonna be angular momentum will be equal to, let's call this direction, I'm going to call it a spin direction, but we can definitely use you can say cylindrical coordinate system if you like. So this will be the z-axis and x-axis this way, maybe the y-axis is that way in the bottom, and this direction in which this point of contact is angle, say phi. Then we'll have a L along z, let's call it z, along k hat direction, so plus L along this direction, L along say phi direction, and the unit vector along that direction will be cosine phi, which is, of course, is going around in time, so phi is a function of time, I hat plus sine phi j hat. And now we need to figure out what these guys are. And what is phi of t? Phi of t was depends on what t equal to 0 is say omega t. So t equal to 0, maybe it was pointed towards the x-axis. A point of contact of disk on x-axis, right? So that's a t equal to 0, then it will be like that, and I don't need to belabor the whole thing. This whole thing here is just a unit vector, say u hat, which depends on time t, because this angular momentum direction is changing, so it's going to be dependent. How about L phi? L phi is just rotating, so L phi will be, let me draw a nice picture. So we'll have in this direction, that's the axis of rotation, and it's rotating like that. So if axis is pointed out and I'm going right hand rotation, so if I do right hand, then this L is pointed in that direction. And so this is a positive axis, this will be negative, and I will get it's very simple, moment inertia I and the omega in that direction, omega vector in that direction. And so the omega vector in that direction is the omega we found out. Omega was r over r omega in magnitude. So the direction, so it's all negative. So this is positive vector that way. So I pick a minus sign to make it in opposite direction vector to that, and I get I times I through the center, I through this axis, and times little omega. That's this guy, and this becomes minus half m r square omega. So this is that part we already found. How about LZ? To find LZ, it would be using again right hand rule. Is pointed in the positive direction, so this is in the positive direction, so it's a positive direction of the same vector that, and LZ going to be, this is the axis. So for this rotation, we'll have axis while the disk is here, axis is here, and so there is a parallel axis here through the diameter. So this is the axis through CM, and the distance between these axes are capital R. So I want a moment of inertia about that. It will be moment of inertia of that plus m capital R square. So this is going to be moment of axis, say axis B. So this will be I about B plus capital M R square, and it's going with a capital omega, so it's going to be times capital omega. So what is about B? This is through unlike this one through the center and perpendicular, is rotating perpendicular, but this one is actually through a diameter. So this one is 1/4 for the disk. The formula for this is I for this axis is 1/4 mr square. So this is little r square. This radius of this thing is little r square. So what we have is 1/4 m little r square. So this whole thing I can now put together. So the L will be equal to 1/4 m little r square plus capital M capital R square omega. This is the center of mass motion in the k hat direction, plus, actually it's a minus minus 1/2 m r square little omega, and this is the spin motion, and the unit vector, this whole thing times the unit vector is a cosine phi of t I hat, this thing I hat, plus sine phi of t j hat. So that's the unit vector direction, and you can say I put plus here, then we can just put this guy, this whole direction minus. Okay, and this is just minus u hat. So what's the magnitude? Magnitude direction will be square root of this square plus this square, because these are unit vector. So 1/4 mr square plus mr square square, that's LG square, plus 1/2 mr square omega square. How do I get the direction? Let me erase this so I can come back to it. For direction, so we have L, LZ k hat plus LS minus u hat. So we have this kind of u hat is in, say, xy plane, so this is u hat, and minus u hat is in that direction. So this is where the shaft is this way. So this is u hat, and k hat is in that direction. So we will have to complete this. We can say the direction of this angular momentum is in this direction. So we can call this angle, let's call it alpha. And so the alpha will be arctangent inverse of this over this. So LZ over LS. And of course, you already know this LZ is simply 1/4 mr square plus mr square, and LS is 1/2 mr square, this times big omega and this times little omega. Okay, so that's the direction. You might want to check. I'm going to leave you as a question for you. Is L in the same direction as omega vector of the disk? So this is net of the disk. So what is the net? Say this net will consist of omega into k hat plus little omega minus u hat. So you can see that is this they're the same direction or not, that you can answer based on that. Okay, so sometimes people ask that question, and that's something you should be able to check, since I already know all the directions. Okay, now I'm going to do part C. All right. Okay, so to do C, we have to have the same kind of decomposition. So kinetic energy will be kinetic energy of the spin and kinetic energy of that. So kinetic energy of the spin part plus kinetic energy of the around the orbital motion. This one is very easy. We already figured out, and this is omega spin vector dot L of the spin vector. So this is for the spin part, what the spin angular momentum and dot product is, and then half omega of the orbital. Thinking with the vector, this is actually this omega k hat. So this one is that, and this one is omega minus omega u hat from the last problem, and this times dotted into L of around the orbital. So this one is simply LZ k hat. So when you work this out, let me just do this thing, minus omega u hat dot ls minus u hat, that was the direction, plus half omega k hat dotted into lz k hat, and all these unit vectors are the same because already separated, so this half omega minus cancel out. So I about the spin axis, omega square plus half lz, let's call it I about the orbital axis, omega square. And we already got this when we're working out the angular momentum. So I of the spin part was half m little r square, and I of the orbital part came from the parallel axis theorem, a quarter mr square plus m big R square. So this is using parallel axis theorem, and axis through CM is actually one of the diameters of the disk. So using these, so we using the so this complete our answer for kinetic energy, because we can just add them up simply. Oh wow, this was a big long problem, and I hope you learned a lot from it. You can go back and check what happened when we did this. When we did this part. I've already erased all of that, so can't go over that now. But this was an important component. In here, it was important to separate the motion into orbital and spin, and they are all each vector. It was its own vector, this was its own vector. So I had to work out the vector and then add them vectorially. And this is not a vector, this is scalar, and you can pretty much skip this discussion and can go directly here from separation of the motion. All right, I will talk to you later in another video. Bye.